Have you ever just stopped and wondered how the apps on your phone or the games on your PC run so ridiculously fast? Well, a huge part of that magic happens in this hidden step, this real unsung hero of software development called code optimization. It's the secret sauce that takes good code and makes it absolutely great, efficient, and just lightning quick. So let's get into it. You, the programmer, you write code that other humans can read and understand. But a computer, it doesn't speak that language at all. So when you hit compile, you're kicking off a translation process. But what does that really mean? Because, it's way more than just a simple word-for-word swap. You can think of a compiler at its most basic level as a translator, right? It takes your source code and it turns it into machine code that the processor can actually execute. But here's the thing. If the compiler just did a literal direct translation, well, the code would be pretty clunky. It would be slow, inefficient. It'd work, sure, but it wouldn't be pretty. And this is exactly where the compiler's secret mission comes into play. See, it doesn't just want to be a translator. It wants to be a master editor. After it figures out what your code is supposed to do, but before it spits out the final instructions, it goes into this special phase to just polish and refine everything. And that's the optimization phase. This phase is all about a technique called, you guessed it, code optimization. The compiler takes what's called intermediate code. That's a version that's kind of halfway between your source code and the final machine code, and it just makes it better. It'll rearrange things, get rid of unnecessary lines, and basically make the code leaner and faster, all without changing what the program actually does. And the goals here are crystal clear. The optimizer is like an efficiency expert for your code. Its job is to cut down the time it takes to run, shrink the memory it uses, and just generally make the absolute most of every resource the computer has. In short, it's all about getting the smallest, fastest code possible to do the maximum amount of work. Now, a process this powerful can't just go running wild. You can't just have it changing things willy-nilly. To make sure this whole editing session doesn't accidentally break the program, this mission has its own strict set of rules. Think of them as the 3 golden rules of optimization. And let me tell you, rule number 1 is absolutely non-negotiable. The optimized code has to produce the exact same result as the original, no exceptions. Second, it has to actually be an improvement. I mean, what's the point otherwise? And finally, the optimization process itself needs to be pretty quick, so it doesn't just grind the whole development cycle to a halt. And this quote just brilliantly sums up why that first rule is so important. It gets right to the heart of the challenge. I mean, anybody can make code fast if you don't care about it being right. The real genius of an optimizing compiler is making code faster while guaranteeing it stays 100% correct. Okay, so how does a compiler pull all this off while playing by the rules? Well, it uses a whole toolkit of really clever techniques. Let's take a look at just a few of the most common tricks it has up its sleeve. First up, we've got a technique called constant folding. This one is one of the simplest, but also one of the most effective optimizations out there. The basic idea is just to do any math that involves constants at compile time, so the computer doesn't have to waste time doing it every single time the program runs. So the optimizer sees an expression like 2 times 3. It knows that 2 and 3 are constants. Their values are never going to change, so the result is always going to be 6. So it just does the multiplication itself and replaces the entire calculation with the number 6. Bam! Precious CPU cycles saved when the program is actually running. Next up in the toolkit is dead code elimination, and this is pretty much exactly what it sounds like. The optimizer hunts for any code that has zero effect on the program's outcome. Code whose results are never used or code that can never even be reached, and it just deletes it. Here is a perfect example. The variable x is first set to 5, but then on the very next line, it's immediately overwritten with the value 10. That first assignment is never used for anything, so it's dead code. The optimizer spots this, eliminates that useless instruction, and makes the code shorter and more direct. It's like spring cleaning for your code. All right, our third technique is called strength reduction. This one is all about swapping expensive operations for cheaper ones. On a CPU, some operations, like multiplication and division, are actually pretty complex and take more time than simpler ones, like say addition or bit shifting. And this is a classic example. Multiplying a number by 2 is mathematically the exact same thing as adding that number to itself. And since addition is a way faster operation for a processor than multiplication, the optimizer just swaps that stronger operation for a weaker, more efficient one. The result is identical, but it gets there faster. Now, these little tricks might seem small on their own, but when a compiler applies thousands or even millions of them to a huge codebase, the combined effect is absolutely massive. So let's zoom out and see why this invisible process is so fundamental to, well, all of modern computing. The techniques we've just talked about, they're really just the tip of the iceberg. The world of optimization is vast, and it includes some incredibly sophisticated strategies. We're talking about totally restructuring how programs handle repetitive tasks, or tailoring code to take advantage of a specific processor's unique architecture. It can even involve rewriting code to run on multiple cores at once through something called parallelization. So what's the key takeaway here? It's this. Code optimization is that silent, powerful engine running under the hood of pretty much every single piece of software you use. It's the reason complex apps feel snappy and responsive, and it's why graphically intense games can run so smoothly. It's this essential, totally invisible layer that makes our digital world possible. And that leaves us with a really fascinating question to think about. As our processors become these massively parallel beasts and our software just gets more and more complex, the science of code optimization becomes even more critical. So how are these techniques going to evolve to power the next generation of artificial intelligence, of scientific computing, and whatever comes next? That's where the future of performance is being written right now.